Hello and welcome to day 19 of my video journey to acing the interview. I'm recording this a day late, so um, the date is a bit off. Question number 909, Snakes and Ladders. You're given an n by n integer matrix board, where the cells are labeled 1 to n squared in the Boustrophedon style, starting from the bottom left of the board and alternating directions each row. Um, okay. You start on a square 1 of the board. Each move starting from current do the following. Choose a destination square next with label in the range of current plus 1 to the minimum of current plus 6 to n squared. The minimum is because we cannot exceed the max cell in the board, which is n squared. So, okay, we're going to be iterating from, so essentially emulating a dice roll from 1 to 6. Um, this choice simulates a result of a standard 6-die roll. There's always at most 6 destinations, regardless of the size of the board. Makes sense. Not always 6, but at most 6. If the next has a snake or a ladder, you must move the destination to the destination of that snake or ladder, otherwise you move next. The game ends when you reach square n squared. So when you reach the last cell. A board square on row R and column C. A board on square row R and column C has a snake or a ladder if board, so the parameter that we're given, on row R and column C is not -1. The destination of a snake or a ladder is board C. Okay, so in this here, the value of this cannot be -1. It will be another cell within the board. Squares 1 through n squared do not have, squares 1 and the last cell do not have snakes or ladders. Note that you are only to take a snake or ladder at most once per move. If at most once per move, that means that there can't be a snake or multiple ladders. There can't be a cell that both has an ending ladder and a starting ladder. Okay, makes sense. Hope that helps us somehow. Note that you only take a snake or a ladder at most once per move. If the destination to a snake or a ladder is the start of another snake or a ladder, you do not follow the subsequent snake or ladder. Oh, so this is possible. You're just not allowed to take it. For example, suppose that board is -1, -1, 4, -1, 3. On the first move, your destination square is 2. On the first move, your destination square is 2. You follow the ladder to square 3. I don't understand this. This should become more apparent maybe in the examples. Return the least number of moves required to reach the square n squared. Cell n squared. Let's call it cell. If it's not possible to reach the square, return -1. Here we have a couple of examples. Okay, so this is the style that they were talking about. I'm not going to try to pronounce that, but chutes and ladders style, where you essentially move in a zigzag formation starting from the bottom row, ending on the top row. So I'll show you how to get the row index and the column index. And then there's another thing to this, which is alteration. It's zigzag, so we'll need to essentially, okay, well, before any of that, let's look at the example. So This is the most bottom row, I presume, and it has a -1, then a 15, going to the 15th square, then -1, -1, -1, then -1, -1, -1, -1, -1, -1, then -1, all of a sudden 35, that's 14, -1, -1, 13. So this is a snake going back. -1. These two rows are completely empty, but the rest of the rows are empty. And the amount of moves that you can take is 1, 2, 3, 4. Makes sense. Constraints. Let's see if there's anything given in the constraints. Okay, this is a square. It's always a square. The outermost dimension is length is n, and the innermost dimension's length is also n, so that means it's a square. N can't be larger than 20. For it is either -1 in the range. Okay, makes sense. The square labeled. This just means that the board, if it's a snake or a ladder, it is in between 1 and n squared. The square labels 1 do not have any letters. Okay. So what do I think when I see this problem? I I want to iterate over all possible moves, right? I want to start at this cell and go all the 6 different ways that I can. 1, 2, 3, 4, 5, 6, and so on until I reach the last cell. Starting cell, ending cell. Now, how would I be able to also keep track of the moves that it takes me to get to any certain cell? Right? That's the question that I am asking. Well, I could potentially have an algorithm that finds the shortest path and then smartly somehow figures out how what is the minimum number of moves to execute the path that I've traversed. And that would be something like DFS, right? Where you deep first search, where you essentially go and traverse all different paths until you find the one that you actually care about. But then you would also need to traverse all other paths which end at 36, or which end at the ending cell, because you also need to find the minimum. So if this is some kind of search, I'm thinking between DFS, deep first search, and BFS, which is breadth first search. One thing about breadth first search is maybe we could emulate moves somehow with breadth first search. If you guys know what that is, breadth first search means that if you have a tree, then instead of going down to the leafmost node first, you first explore all children of your current node. And what that brings to mind immediately is the first step, the first breadth search, I would explore all children of the node that I'm currently standing on, and I could mark them as move 1. And if I could mark them as move 1, as in it takes me 1 move to get there, because the move would essentially be a roll of the die. So then a continuation of exploration of starting from one of those nodes, the child would be equal to two moves, right? So a breadth first search approach seems to be more reasonable because in the process of searching, I'm also keeping track of how many steps I've made in order to get to a specific point. So if I was to do a breadth first search, I would first need some kind of structure. An array could be fine with of length n squared that would keep track of visited and unvisited nodes. So let me start with that. Right off the bat, I don't know if this is actually what I will be using, but let's hope so. I'm adding a 1 because I don't want to do weird conversions from like this distance to a 0 indexed board. I'm going to keep it 1 indexed just because this whole board is 1 indexed. Now that I have this dist, let's implement a queue. A queue is usually used to, just so you know, iteratively implementing breadth first search is done using a queue, where you append to the end and you dequeue you enqueue from the right, you dequeue from the left. I usually do it using a list, and then while queue, I'm going to say current is equal to queue pop the 0th element, and for next in range current plus this is me implementing the next moves that I'm going to be doing. So range from current to, what was it? Minimum of current plus 6 and n squared. Let's have an n because len board n squared. This is a notation for putting something to the exponent. So n to the power of 2. And since range is inclusive on the bottom, exclusive on the top, we're going to add a 1. And for next, I now have to find I have to figure out which where I am on this board, like what sort of, what would it be, destination, board, I have to figure out somehow what element is in the next field. Okay, so actually, let's hold off on this. I think we have something going here, but we're clearly missing some sort of intermediate functionality that's going to let us quickly identify what's lying in the next of, or what is in the next of board. So let me actually, what do I need to do that? Let's have a cells array of also the same length and say, okay, this is what I need to do. I need to have an intermediate structure that it doesn't have to be a structure, it could be a function too, but I need a very fast way to identify um, what is this int value in this board on position, let's say like 2 or 3 or 4 or any next. So I'm going to have an array, a regular array, with tuples inside it that tell me which row and which column I need to look for in the board to get whatever number I have, whether it's 15 or -1 or -1 and so on. So I'm going to say for I in range starting from, well, actually I just need to do this from n to range 2 because I have that many elements. I'm going to say row is I by n and column equals I modulo n. The double divide sign converts this into an int because originally this, well, a single divide sign will return a float and without any remainders. So this is a whole number and column. But notice that the weird structure of this board makes it so that these aren't the real rows and columns. So let's say that row adjust is actually n minus 1 minus row. N minus 1 because we're 0 indexed, and call adjust is equal to column if let's see, if row adjust modulo 2 is equal to 0, meaning that if this is an even, it will always be going to the regular pattern, to the right. I realize I'm looking at the video, it's showing the wrong. But else, it's going to be n minus 1 minus row. So else, we're going to start from the right side and go to the left. Now that we have this, now that we have the real row and the real column, let's add it to our cells. And now, since we're finding, let's keep them all one indexed, so there's less confusion. Adjust and column adjust. Let me print this quickly just so I know what it's that we're looking at the roughly the same, the correct pattern. 5 5. This is already wrong. Column should be 0, right? Column should be 0. This is column. Is that it? The first element should be a 5 0. I modulo n. My row adjust. Column, if the row is an even number, then it's 5 0. So okay, 5 0, 5 1, 5 2, 5 3, 5 4, 5 5, 4 5, 4 4, 4 3, 4 2, 4 1, 4 0. 3, 0. Okay, perfect. So this is our cells. We can now easily identify which where to look in board for a specific position. Okay, perfect. Now that we have this, and we have a distance array of the same length as our cells array, let us so the queuing mechanism. So how does the queue help in breadth first search? The approach here is this, that we enqueue the first element, which is in my situation 1. We enqueue the first element, and then we explore all of its children. Its children, in our case, are just 1 through 6, right? Because we can go to 1, 2, 3, 4, 5, 6, 2 through 7. However, the first element, if we were just to throw the dice number of 1, we would immediately go to 15. So let's say that, let's call this destination. Right? We need to know the row. We need to know where our next cell is going to be. Let's say row column is of cells next. And now destination is equal to next if board row column equals -1, else it's going to be the board and the column, right? Because that would mean that we've either hit a chute or a ladder, or a snake or a ladder. So now that we have this destination, okay, we have a destination. If it's not been visited, if destination is not -1, then don't do anything. So what would we do if it is -1? If it is -1, if it is equal to -1, record that I have, what would this be, move? If destination is equal to -1, meaning that I have not yet been there, 15, then say that that is my first move. Okay, so move is equal to, I'm already there, so I can say that distance of distance of next is equal to distance of current plus 1. The distance of this is the distance of the first is going to be 0. The distance of the first is going to be 0. Distance next. If it's not been visited, then add 1 move to the next, and then and that's it. Return. We have a distance array, right? So we can do distance n squared. If in the breadth first search process we never hit the last element, then we are screwed, which means that all the different traversals that we've done, we weren't able to reach the last key, and we're going to get a -1 there. However, via this function here, if we were able to get to 36 or the last square at any point of time, it would possess the number of times it took to get there. Also, what about, I wanna talk about this a little bit because some of you may be thinking, or actually, not just some of you, even I'm thinking that what is the justification for, let's say, only doing this process if the node has been unvisited, right? What is the, hold on, output -4. 1 second, let me finish my train of thought. Why is it okay to only assign the number of moves to take to a certain square if we have not visited yet that square? The answer to that is the property of breadth first search, which is that the children nodes are first visited from its parent, meaning that the first time we're visiting any sort of node is guaranteed to be, the first time we're visiting any node is guaranteed to be the quickest path there, if that makes sense. Let me repeat that. The first time visiting any sort of node is guaranteed to be the quickest path there, which means that we will get to 15 multiple times. We'll get to it by hitting 2. We'll get to it by hitting 6 and 3. But the first time we're hitting it, it only took us 1 move, whereas the second time we're hitting it, it's going to take us 3 moves. So we'll never have to update this value again once it's set. And that's the beauty of breadth first search. We're traversing children, we're traversing the first possibilities first. Okay, so now why didn't this work? I'm never enqueuing, first of all. So enqueuing is queue append queue append next. Okay. Still wrong answer. Output -1. Interesting. Where did I go wrong? For next in range of current plus 1 inclusive to minimum of current plus 6 to n plus 1 row destination is the destination in the index, but the -1 is actually in the board. Destination is in the board. Submit this. And we have list index out of range board destination is out of interesting. Where am I hitting a somewhere in here I am messing up a single value or something. Let's just print it. It was here, so let's print destination. See where this puts us. 15. Not board. Distance. Okay. We got 1. What about for the first one? First one. Oops. Let's remove the print. Run. Expected 4 output. Output 6. So we're already getting something. Let me see where I messed up an index here. I was thinking that since I started no, I started at the right. Oh, did this work? No, it didn't. 6. Okay, we're very close because we have the right answer here. Where's 6 coming from? I want to see the distance matrix, I guess. Distance matrix starts with 0, and we're never able to visit one of these. Doesn't seem right. Something is off in the maybe the destination seems to be not working as if. The destination if does not equal on else next. Why am I not? Why is 15 not 2? Where's 15? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Why is 15 not 1? 15 is not 1 because once I get a next, the column if we should be printing out a 15 here. See if this actually. 15 is the first, right? 15 is the first. And 15 of the distance matrix is equal to -1. And since it's equal to -1, the destination should be equal to the value, the destination, not next. Next is, so again, it's part of Scream architecture where you have to kind of name things the way that they are. Okay, and this is going to be this one. Submit index out of range. Oh, no, I decided that it's going to be expected 4, output 6. distance current plus 1 and append again destination because we're okay, so yeah, it's very apparent that something new doesn't come off as easy when you're implementing it. I want to know what these solutions are. By the way, if you want to see the solution here, this is our solution. See how it's done so much faster. Well, for one, the memory that I can make a quick comment on, the memory save would be to not implement another data structure to keep track of where we are in the board. A way better and maybe memory efficient approach is to have a function where you feed it an index, and it immediately tells you which rows or columns we are. But let's see some of these faster approaches. There's also an algorithm called the Dijkstra's algorithm, and I'm wondering if any of these are actually utilizing it. I don't know it, so I don't even know what to look out for. This looks like an NQDQ. They're identifying the board as B, reversing it, then enumerating through. Yeah, unfortunately, I don't know. Okay, so I'm guessing more questions related to similar ones are coming up next, so watch out for these. This video is taking a little bit too long, so I'm going to end it here. See you guys later. Bye.